Hi, I'm Christoph Hemmer, and I'm happy to present our paper on optimal recurrent network topologies for dynamical systems reconstruction. Therefore, I work together with Manuel Brenner, Florian Hess, and Daniel Dustewitz. Dynamical systems reconstruction is an area in machine learning in which one tries to understand and model complex systems or dynamics that evolve over time. These systems-driving equations are generally unknown, and one is left with the observations, from which the main goal is to infer a generative model which is able to reconstruct the observed dynamical system. These reconstructions should align geometrically, measured in terms of the Kullback-Leibler divergence, and temporally, measured by the Hellinger distance between the observed and generated power spectra. For our reconstruction models, we focus on a specific type of recurrent neural network known as the piecewise linear RNN, or PLRNN. Training is done via standard backpropagation through time using a mean-squared error loss, where we additionally use a sparse teacher forcing protocol in order to tackle the exploding vanishing gradient problem. Besides the PLRNN, we also tested our methods to other standard architectures like LSTMs or vanilla RNNs. Often in machine learning, we are interested in sparse models with low parameter load to improve efficiency and interpretability. The standard strategy for this is parameter pruning, via removing those with small weights. Based on that, the so-called lottery ticket hypothesis was proposed, stating that in a neural network there exists a subnetwork that, when trained in isolation, performs almost as well as the full network. This subnetwork is extracted through iterative pruning, where one retrains and prunes the network until the desired sparsification is achieved. While standard pruning relies on weight magnitude, in dynamical systems reconstruction, small weights can significantly impact performance. In fact, when looking into the individual influence of a single weight to the attractor's geometrical reconstruction, there is no big difference in small and high weight values. Therefore, we introduce our new method called geometry-based pruning, which removes weights based on their impact on the attractor's geometric shape, measured by the change in KL divergence when removing that weight. Our experiments on different data sets, including the Lorentz 63 system and real-world ECG data, show that geometry-based pruning and not magnitude-based pruning consistently reveals the best performing subnetworks in both measures, the state space and Hellinger distance, even though the Hellinger distance does not influence the pruning criterion. In fact, in some cases, there is no statistical difference between removing weights by magnitude and randomly. We also find that our approach works well in the case of other architectures like the LSTM tested on the Lorentz 63 dataset. In the lottery ticket hypothesis, the initial weight values in conjunction with the network topology is crucial for the subnetwork's performance. To test this in the context of dynamical systems reconstruction, we reinitialized the initial weight values and observed not much performance difference, highlighting the crucial role of the network topology. Translating this topology into a graph reveals hub-like structures with highly connected nodes, as well as small world characteristics given by the short average path length and the high clustering. The understanding that network topology is crucial and contains specific characteristics enables a reverse engineering of the problem. By creating an algorithm that replicates the topological properties observed in the pruned networks, this knowledge can be used as a prior embedded in the network's topology. Therefore, we propose our GeoHub algorithm, combining the characteristics of hub and small worldness with the Barabasi-Albert model framework, to generate a directed graph that reproduces the observed network topology. We then compared the reconstruction performance of different topologies in the network and found that models initialized with the GeoHub topology demonstrate superior performance and faster training across multiple datasets. Therefore, we conclude that network topology alone is sufficient to produce highly sparsified and well-performing networks in dynamical systems reconstruction. Thank you for your attention.